Good morning, everybody. Welcome back to the Flash tutorial. So today I will essentially walk you through a couple of applications and implementation of zinc particles and the way one can use them in the Flash code. So I guess Eve did already quite a good job yesterday in motivating why you want to essentially mess up your hydrodynamics and MHD, which tells you all about the physics. Essentially, mess it up, putting it zinc particles in your simulations. And the reason is mainly, for does it work? The lights too bright.
Second.
Yeah, thank you. So the reason is that, in particular, if you do simulations in the realm of star formation or similar, where you deal with collapsing objects, eventually you don't want to resolve certain regions anymore. Otherwise, your simulation grinds to a halt, and you can only follow most probably a single collapsing region, whereas you are often interested in entire star forming cluster, different regions which are collapsing. And this problem already was noticed by almost 20 years ago by Matthew Bate, and he implemented this kind of technique in his code on SPH simulations, essentially replacing dense regions of gas with essentially black boxes, black holes if you like. And so that gives you somehow a control, if you like, on what is called the true love criterion. So you're not violating, or if you violate it, you do it deliberately, essentially violate the so-called true love criterion. I will we'll talk about this a little bit later in a bit more detail. So essentially, you want to always make sure that your physical length associated with a collapse, namely the Jeans length, is at least barely resolved. And here the typical number is 4, but you can imagine 4 is a really small number if you think if your physical length should resemble a wave, or so you essentially resolving your wave with 4 grid points, which is it is barely resolved at the end of the day. But it's a minimum criterion not to get spurious fragmentation in your simulation, at least for grid codes. With this technique, which I will talk about, you are able essentially to do a long-term run of collapsing regions where you have, for instance, different individually collapsing cores, if you like, and can simulate binaries, stellar clusters. But they are also useful essentially for if you model something like subgrid type feedback mechanism. If you take the information which you can collect in your zinc particle and feed it back essentially onto your grid, into your hydrodynamics, for instance, outflows or supernova explosions alike. So they can be quite useful to implement a more or less self-consistent model of feedback. So that's the motivation, but we still essentially have a problem, because we are, by hand, more or less deliberately violate our hydrodynamics, and we place high-density region or replace high-density regions, and I'm talking here about zinc particles which have a size, so they are not negligible in size, a couple of grid cells. So we are kind of violating these high-density regions, and the question is, how to interpret these regions, how to interpret actually the zinc particles if we have once formed them in our simulations. And you can imagine that depends already on the size of your zinc particles. So if you like, if you simulate smaller cores with a few fragments, they can actually represent something like a protostar, if you like, if they're smaller, if your zinc particle is smaller than, say, a tenth of an AU or so. But if you do more global simulation, go to larger scales, try to simulate the formation of molecular clouds, for instance, you can't afford, essentially, not by now at least, to increase the resolution all the way up to a tenth of a parsec or so. So you want to replace essentially regions which are much bigger, maybe up to a parsec. And then, of course, a single collapsing region is then not a single protostar anymore. So it's at least a small stellar cluster. And the same is true for some intermediate scale. So at least what we can say, if we come up with a recipe to introduce zinc particles in MHD or hydro simulations, including self-gravity, they are essentially bound objects or bound collapsing regions, which a fraction of these gas will most probably turn into stars, or maybe, if you're interested, into planets, if you want to form them in protoplanet disks by gravitational instabilities. So this is essentially the only thing you kind of know, that you have a bound collapsing region, or you catch a bound collapsing region, which a certain fraction of the gas will form into stars. But that's about it. Sorry? Oh, sorry.
I'm sorry. So a zinc particle is not treated as a point particle in the simulation? It actually has...
It depends on the recipe, and the recipe I'm telling you has a certain size. It has a size of, if you like, of influence, and we call this accretion radius. So this is essentially the radius where we allow the gas to be accreted on our point particle. So it has a size of influence, if you like.
Okay, so it's numerically and philosophically very different than when they put star particles in these galaxy simulations.
It's not very different, but I mean there are different ways to implement them, and of course, an infinitely small particle doesn't help you much, because you want to be connected essentially to your hydrodynamics. So somehow you have to come up with a recipe to assume a certain size and size of influence essentially to your star particle.
I'd say the main difference between cosmological star particles and zinc particles is zinc particles continue to accrete over, so with cosmological star particles, you create it, you're done, that's it. It's instantaneous. Zinc particles continue to accrete over, and you resolve their growth in time. And that means that they need to interact with the hydrodynamics continually, and so you need to define a radius over which that interaction occurs. You can't, as is common in cosmological recipes, just say, well, all right, I take some gas out of this cell and turn it into a particle.
So it's kind of similar to what they do in the supermassive black hole simulation?
Yes.
Yeah, similar. Thanks for clarifying. Okay, just to give you maybe you have seen a couple of these type of movies. Here's a movie from Paul Clark on this SPH simulation, where you see the zinc particles appearing essentially as protostars, if you like. So this is a cluster of maybe a tenth of a parsec, and it forms a bunch of stars. So you form you form a stellar cluster, or even multiple stellar clusters. And they interact, of course, gravitationally, and they, as Mark said, they accrete gas while while the entire turbulent cloud core here is collapsing. So there's a typical application. Here's an application on larger scale. So we are talking about a formation of a molecular cloud core in what is called colliding stream simulation. So some numerical experiments where you convert essentially H2 gas into molecular gas, and in the same process you start to form stars. And as you see here, you also form, of course, self-gravitating regions, and these black dots, the zinc particles, essentially, they are, can't be interpreted anymore as individual, say, protostars. So they are already little stellar clusters which grow up to 100 solar masses or something. So the interpretation is always a little bit up to you at the end of the day. So now we are talking about essentially the implementation, the particular implementation here in the flash code. And particles were actually introduced at very early versions already in the Flash 2 version by Paul Ricker, essentially being dark matter particles. So they could interact gravitationally, but you had to put them at the very beginning of your simulations, and they didn't accrete gas, so they weren't, apart from the gravitational interaction, not very dynamic. But all this nice thing on this module is you can build on it easily, do a more dynamic implementation of zinc particles, so create particles on the fly when there's a collapsing region, because Paul Ricker's module already had all the framework essentially handling particles or combining particles with the flash setup or with the flash environment, and dealing, for instance, with, if particles, if you have a periodic simulation box, for instance, your particle, if it moves out on one side, it comes in on the other side. All these things were kind of handled in this earlier particle module already. And also, if one particle moves from across CPUs, this is also some bookkeeping you have to do, and this was all essentially ready. And then on top of this particle module, essentially Christoph Federath implemented the zinc particles, which I will represent here. So the main difference is you could create then particles on the fly, defining and depending on the criterion you use when you want to create a particle. It used a different method to for the gravity, so for the gravitational interaction. So Paul Ricker's original method essentially projected a particle mass as a density onto the grid, and then solved the Poisson equation, for instance, with the multi-grid solver, which we were talking about yesterday. And whereas here, because we assume for most of the cases we have only a few meaning maybe up to 10,000 or so of zinc particles. We are not talking about tens of millions of zinc particles. Then this method, so essentially Christoph's method, essentially would break down or would be just way too slow. And then they can be created essentially on the fly. They can accrete mass while mass is attracted toward the gravitational center of a zinc particle. And he introduced also a couple of technical steps, some subcycling if you have closed binaries, for instance. And of course, there's also an interface, essentially, if you want to implement your favorite feedback model, like you want to have a subgrid model for outflows, or on larger scales, maybe supernova feedback. And there's also, because, as I said, we are dealing usually with only a decent number of zinc particles. There's also a global list of particle list distributed on all CPUs. So this is essentially the implementation of the gravitational interaction. So this is what they do. Or why we replace them, because they still interact gravitationally with the gas, and of course the gas has influence gravitationally onto the zinc particle, apart from the fact that they also get momentum when they accrete and so on. But just stick with the list here of the different types of gravitational interaction we have for if you have a simulation with zinc particles. Of course, we have the usual gas-gas interaction. There's no modification needed. So this is just solving the Poisson equation the way you like it, either with a multi-grid or with the tree-based solver. Then you have essentially interaction of the grid. So the mass on the grid has, of course, an influence on the gravitational acceleration of the zinc particle. And this is done with essentially a direct summation, because we have to walk through the grid anyway, dealing with the particles. So this is not very expensive. And of course, the particles have a feedback on the grid gravitationally. This is also done by a direct summation here. And of course, the particles interact with themselves. This is done with a similar way. And all the 1 over r square acceleration terms are slightly modified with a so-called softening approach, and with at a given softening radius, because all these formulas diverge if the distance between, say, two particles or a particle and the center of mass of or the cell center of a grid point approaches zero, then the gravitational acceleration diverges, and this is something you don't want. So there are different ways to do your gravitational softening. This is essentially done by a parameter in your flash.par. And here you see just the way the acceleration changes depending on the method of your softening. And Christoph has his best experience using the spline type softening. So that's a fairly complicated curve here, depending on the distance of a zinc particle and a grid cell, or a zinc particle and a zinc particle here. But you can play around with different types of softenings here. So, and of course, if you once have the gravitational acceleration, you advect your particles according to Newton's law here. And there are also different ways to do this. There's a very simple forward Eulerian method. And as you see here, how that's just the simplest way you can essentially think of how to advect your particle. So you update your position and the velocity of your particle. So this is not really recommended, because this is it doesn't give you stable orbits for a long time. So, but for quick testing purposes, you can maybe use this. And a much better way, I will show you some results of advecting or advancing your particles, is this method of a variable time step leapfrog mechanism or method, where you use half time steps to move your particle along. And this is second order accurate and gives you very good stable orbits for a long time. Nevertheless, I mean, you can ask yourself, what should this time step be? And of course, if particles approach each other if they come very close, you have to account also for the typical time step of zinc-zinc interaction, or even zinc-grid cell interaction, if the acceleration gets too big. And this is done essentially by introducing a new time step. This is necessary, of course. And this time step, so the time step due to the gravitational acceleration here on zinc particles can be much smaller than the typical hydro time step, and hence you don't want to evolve all your simulation on a time step which can be really small if you're talking about a closed binary. So hence there's an subcycling introduced into for this gravitational interaction of particles here. And of course you do n cycles until you reach again the global time step for your entire simulation, the hydro time step. So this is often the case, if you introduce a new physical module, your physics you're implementing usually reacts or acts on an individual time step, and this is the same idea here. So your sinc particle interaction due to gravity acquires its own time step, and you have to account for this. So this is, for instance, an outcome, how important it is essentially to really use an individual time step and do the subcycling. You see how quickly, and these are essentially only 10 orbits, how quickly you move away from your real solution. So you shouldn't have a perihelion shift here. This is just a Newtonian problem of two particles orbiting each other, and hence you with the subcycling and the leapfrog approach, you get a fairly good result here. And you can actually continue this. There's a different setup. So essentially, two particles being here or here, orbiting each a common center, and this is the result. After I could even show a movie, it would look exactly the same, just a circle. After 1,000 orbits, they are still on a circular orbit, which is good. So this is, there's another example, of course. So these examples were essentially only sinc-sinc interactions, so gravitational acceleration due to sinc particles, but of course the gas has also an influence, and what you see here is essentially the result of the gravitational potential due to a gas distribution. This is a singular isothermal sphere, more or less singular. You have to cut it off at the very center here. But and particles, if you initiate them with the right velocity, again should go around in a circle. And what you also see here in the simulation, how, because there's a refinement criterion linked to sinc particles, meaning that you want to always refine or always be at the highest refinement level wherever you find a sinc particle. I mean, this is more or less done automatically if you use a Jeans type refinement criterion anyway. So hence these regions become refined wherever a sinc particle is. So here's essentially the result of the orbits for this type of simulation for up to 100 orbits, and they all go nicely around in a circle. So the gravitational interaction works pretty well, at least for this, for the cases you can really test it, for the simplified cases. Now we want to talk about essentially the approach. You really invent these sinc particles, namely you want to create them on the fly whenever you catch essentially a self-gravitating region, and this is done by a multi-step process. First of all, you scan your grid and ask yourself if a particular grid cell exceeds a density of a critical value, which is just a parameter essentially here. And if you find such a grid cell, you go through a list of criterions until you really decide you want to have a sinc particle here. And it's clear from, if you go through the list, that what you want to make sure is essentially you want to catch a self-gravitating region, so a collapsing region, not just a density fluctuation, which is created by a shock, for instance, but might not be gravitational unstable. So you want to make sure that all the gas in this certain region around the sinc, so you are using again the accretion radius, is converging towards its center. There's also, you can check for, or what is done, you check for a local gravitational minimum for this density cell, for this high density cell you find, you look in the region whether the region around the prospective zinc particle you want to create is gravitationally bound and genes unstable. And of course you don't want to create a zinc in a region where there is already one, so you also check whether there's a nearby zinc particle already. And if all these criterions are fulfilled, you decide you create a new zinc particle.
Robi,
Yes?
I've never understood the point of criterion 2, because if you didn't violate, if you weren't above the critical density but in the previous time step, right, and now you're above the critical density, so you're going to create a zinc particle, right, well then, isn't div V less than 0 necessarily because mass is conserved? Right, how would it be possible to violate criterion 0 without...
Maybe it's on top, so I
guess it might be possible that you violated criterion 0, didn't create a zinc particle because you violated, because...
I don't know, what happens if you have a shock moving across the, I mean, a shock front being high density moving across your simulation box.
The shock front has div V less than 0. I mean, mass is conserved.
On one, yeah, on all sides, that's right. Yeah, maybe it's a redundant criterion, but yeah.
I've never understood it. Okay. I'm wondering if there's some subtlety.
Not that I can tell you right now. So I know that Christoph is very cautious about these things. So he decided to have this convergent criterion as well. I mean that might also be applicable or for the because you use more or less the same mechanism to accrete gas. So you have this criterion anyway for the criterion to accrete mass onto your zinc particle.
It's cheap and it can't hurt.
It's fairly cheap. Yeah, that's right. I mean, you have to look around your grid cells anyway. So this is, for instance, an example. If you just use a density criterion without any, you create a bunch of zinc cell at every high density region. So that's just to make sure that you're really talking about a collapsing region where you also have for instance a gravitational minimum and so on, all these criteria. Otherwise you get way too many particles here, and you see how they kind of line up just on this filament, despite the fact that the entire thing wouldn't collapse like this. Yeah, and then the newly created zinc particles essentially gets immediately some mass due to the same procedure. Then the accretion takes place, which I will show you in a second. And but there's one thing, for instance, some very subtle thing I have to say, is that you could, if you have a very symmetric setup, and strangely enough, so for instance, you have a singular isothermal sphere where the center is right at the cross points or at block corners, and your domain is decomposed, around these block corners at different CPUs. Then every CPU essentially would create an own zinc particle because all the criterions are essentially fulfilled. And to avoid this, there's an merging essentially of these sinks which you spuriously created just by essentially accident because of this highly symmetric setup. So in practice, you don't have to worry about this much. In particular, if you talk about a turbulent media or so, but if you have a highly symmetric setup, this can happen, and there's actually a mechanism to find the identical particles, I would say, across the different CPUs. Again, for the mass accretion, we find our converging criterion again, and this is again a list of the criterions which have to be fulfilled essentially to create mass from the to accrete mass from the grid onto the zinc particles. And what is done is essentially you just take the excess density of your grid cell and the access to the critical value you put in by a parameter, essentially take the mass and put it into the zinc cell. So you have mass conservation, of course, in your simulation box. And also because the mass parcel is also moving, it gives the particle, the zinc particle, also a kick, so it gets a momentum. So you have linear momentum conservation, of course, in the simulation box. It's a little bit more tricky if it comes to the angular momentum, because it's not quite unique what to do actually with the angular momentum. And there's one possibility you could do. You give the zinc particle an internal spin. So if you add up the angular momentum in your simulation box plus the internal spin of your zinc particles, then you have angular momentum conservation in this sense. In practice, it's just an internal information which you might use if you like, for instance, if you want to implement a feedback model for outflows where your opening angle might depend, for instance, on the spin of your zinc particle. So there's essentially an additional information. It doesn't do anything to the hydrodynamics or anything to the simulation box. You just add up the spin of your individual particles here.
If you're giving spin to the particles, do you take care that no particle crosses the maximum spin, like the breakup spin?
No, I don't think so. We have a check for this. So should actually, that's actually a good question whether one should do an analysis of what happens if they break up. But as I said, it's just a number here. Yeah, Mark?
Yeah, I mean, no, you shouldn't do that because the issue is that, right, I mean, the angular momentum, it's not like all the angular momentum in the material that's around the zinc particle is getting accreted onto the zinc particle. What's really happening is that there's some unresolved inner accretion piece, which is separating the mass and the angular momentum. And it is not, so you should not be assuming that all of the angular momentum is getting pulled off. So you have to, so what you're doing is you're making a subgrid model for what happens to the angular momentum, given that I can't resolve the turbulence in the accretion disk that is responsible for separating out the mass and the angular momentum.
That's right, yeah.
Keeping track of the vector direction.
I mean, yeah, you don't even know how big the object is you are talking about. I mean, you have a zinc particle that has an accretion radius, but this is just a parameter for your scheme you are introducing here. So it's hard to tell, whether you already have a star at spin up, because you don't know what object underlies actually it could be a binary, then you don't have this problem anyway. Yeah, and on top of this, there's an option of merging particles if they come too close, and you can imagine if that might be useful if you're not talking about individual protostars, if you're not talking about objects of less than 0.1 AU, but larger objects which essentially are still just gas clumps, self-gravitating gas clumps, which might undergo even physically some merging. And there's an option you can switch on a switch that if these particles come close to each other, if the accretion radius starts to overlap and they're gravitationally bound and so on, you can merge them if you like. So this you do have this option because it's not always clear what these zinc particles represent. Yeah, as I mentioned at the beginning, so there's a global particle list, so you can collect easily the information of all particles on a single CPU core, and that might be actually useful, for instance, if you want to calculate integrated masses, like the total mass of all the zinc particles. This is actually a useful quantity because this is a fairly robust quantity compared to the mass of individual zinc particles. because the mass of an individual zinc particles depend at the end of the day on the resolution. So it's, whereas the global mass in all zinc particles, you can do a couple of test simulations. This is a fairly robust quantity, which then you can use, for instance, again, if you want to introduce a feedback model, because the entire mass, say, in your simulation box in zinc particles, you could use then and convolute it, for instance, with an IMF, so you know how much massive stars should be there, and so on. So that can be a useful quantity. And of course, on a technical issue, this makes only sense if you have, not too many zinc particles, and we're talking about maybe up to 10,000, maybe 100,000 are still fine without needing too much memory. But up to this number, that's actually all right, I guess. Yeah, let's go through a couple of particle properties you find in the flash code. Of course, you want to know the position and so on. So this is already provided by the main particle module, so the positions and the velocities, and then some internal informations about a unique tag, which might be also useful to use. You can identify each particle in your entire simulation box by a unique tag. Then you might need, and this is for internal distribution mainly, the block ID, essentially in which the particle resides. That can of course change because the particle is moving essentially in a Lagrangian way across your grid simulation, and the processor ID that holds the particle. And of course, if you have a massive particle which interact gravitationally, you need a couple of more properties, and they are listed here. So the mass, of course, the acceleration, and for the leapfrog you also need the acceleration from the previous time step. So that all makes sense. And then additionally, for your zinc particle, you need a couple of more information, for instance, the accretion radius, and then we talked about that we want to store the spin, so the angular momentum, and might be also important to have the mass of the previous time step to, for instance, to calculate the accretion rate onto individual particles. Of course, the accretion time is also can be important. In particular, again, if you want to implement some feedback model where you want to where a single particle should live a couple of million years because it represents a massive star and then goes off supernova, for instance, you can use the creation time to know how old essentially your stellar cluster or your star is. And then there's a big question mark here about the magnetic field. So what should we do with the magnetic fields? And so far it's not done anything, but the properties are already there. So what we find typically in the simulation that because these zinc particles are just a few grid cells across, we do enter a regime where we have quite the magnetic flux is essentially numerically already disappearing, is already diluted, so we don't acquire typically too much flux within a zinc particle radius. So far we don't have a good recipe, so we didn't make our hands dirty at this point. Yeah, Mark?
Well, so I just wanted to clarify. So do you actually change the magnetic field with the magnetic flux on the grid when you accrete matter?
We are not doing anything with the magnetic field. So the mass to flux
unchanged.
Unchanged. It's totally unchanged.
I think that's probably the right thing to do.
I think so, because as long as you don't come up with a good physical model, and as I said, on a numerical, it is dissipated anywhere a little bit on these small scales. So yeah, the magnetic field is unchanged. That's the message here. So yeah, what about this density criterion? Of course, it should be linked to your resolution, and your resolution, your minimum resolution is of course then governed by this true love criterion where you want to resolve your genes lengths. So, and this can be then converted to a threshold density, so critical density, which you might adjust in your simulation if you go to higher and higher resolution. So if you have smaller grid cells, you also can increase then your density, your threshold density. Essentially, you have to keep this in mind, and this is something you have to essentially pre-calculate before you run a simulation to know to what refinement level I want to go, and then maybe use a formula like this to convert it to a threshold density for your simulation, which is a parameter given by this thing here. So this is something you have to keep in mind, that ultimately your threshold density, your parameter is linked to the resolution of your simulation you want to use. And that you actually find this genes refinement criterion within the sinc particle module, and in practice you can use a much bigger number here, just making sure that on the highest refinement, eventually on the highest refinement level, it approaches more like the true love criterion, but in a more diffuse media, you essentially can allow the simulation to be resolved much more just by increasing this number. So the number of grid cells you want to resolve your genes mass. And this might be important, for instance, if you want to resolve during the collapse the turbulence within a gene's length. Of course, you want to have much more grid points than just 4. You want to at least have of the order of 30 to get internal structure within a gene's length. Yes?
In the flash code, how do you make sure that on the highest level you still resolve the gene's length? Do you implement the pressure floor or something? On the highest level of refinement that you want the simulation to go, you still have to make sure to resolve the genes.
So what you do is then on the highest refinement level you go back to and adjust essentially your threshold density, so that you kind of the threshold density is the density at which you want to put in a sinc particle. So no problem.
But you still can violate the gene's condition because of your other conditions. The threshold isn't sufficient to guarantee.
It's not sufficient, but then you are essentially not really violating the gene's criterion, because then you are not in a collapsing region. But it's an overdensity by a shock maybe or something. Okay, I think that's all about more or less the technical stuff. Maybe at the end I have a couple of more slides to this, but what I want to do now is to walk through a couple of tests and examples how to use sinc particles. And here's another test, for instance, where we collapsed a singular isothermal sphere because there's an analytic solution of the accretion rate. And this is what you see here. So we put a sinc particle, here's the accretion radius, and then calculate essentially the accretion rate. And the accretion rate, the theory for the collapse of a singular isothermal sphere tells you, or Frank Shu told us in 1997, that the accretion rate is essentially constant and given, and it is proportional to the sound speed cube over the gravitational constant here. And this is what we find. So the accretion rate is constant and fulfills this the theoretical prediction here. And you can do this for a couple of different singular isothermal spheres. So of course you can imagine that it can't be the accretion rate should depend also somehow on the instability of your initial core, and it's more or less so there's a prefactor which is actually very important here, which is often neglected in the literature, and people say we find something, our accretion rate is C cubed over C. But at the end of the day, it depends quite strongly on the initial mass or the density at the edge of your singular isothermal sphere, given by this, what is called the instability parameter. And the instability parameter determines this prefactor, which is constant if it once collapses, but as you can see in this plot is fairly sensitive, the prefactor on the instability parameter. Nevertheless, we did a couple of simulations, probing different the collapse of singular isothermal sphere, and there's a formula, essentially you can calculate this m naught. Here it's not an analytic formula, but it's easy to solve, and this is done here by the straight line. It's also in the 77 paper of Frank Xu, and what you see is essentially how the simulation results essentially follow these this line here. So that gives you a certain confidence that at least the main feature in a very simplified setup does work. So the accretion rates, for instance, in your zinc particle are exactly doing this, what you expect here. There's another fairly simple test. Unfortunately, there's no analytic solution anymore, and this is something Yves already mentioned yesterday, namely the collapse of a hydrostatic sphere. Of course, you have to perturb it, have to make it slightly unstable, and when it collapses, you get an time-dependent accretion rate, so you get first a boost, and then it declines because eventually you run out of gas and all the material is accreted onto your zinc particle. And what you could do is essentially compare to other numerical results with other codes, and this was already done by Foster Chevalier. I think Yves mentioned this paper already, where they did more or less for the first time a collapse of high resolution collapse 1D of a Bonner-Hilbert sphere. Then there's also a nice test which I recommend to you to test actually, because the setup is within the Flash setup tree, namely the Bose-Bodenheimer test. So what it is essentially a sphere which you perturb with two overdensities with what is called the m equal 2 overdensities, and at the end of the day you should find three collapsing objects, namely one in the middle, and then because of these overdensities become eventually gravitational unstable, and at this point you also should find zinc particles, and this is something Christoph also tested here, and you can see here the result. And of course they tend to approach each other because the thing is still gravitational unstable and gas is flowing towards the center here. And I think there's a little animation on a very coarse resolution you see, and here there's actually two more particles appear if you run the simulation for longer, because there's more spiral features showing up at the edge of the sphere at later times. Yeah, and we did also a comparison with an already implemented scheme of zinc particles within the SPH approach. And this is how it looks like. And if you watch the two movies here carefully, you see that particles more or less appear at the beginning, at least, at the same spots, and you get more or less the same structure. Whereas you see a little bit in the Flash code, you get a little bit more structure in the low density regions. So that tells us that with this particular resolution, at least, the SPH simulation is a bit more diffusive. Hence, it also collapses a little bit further. But nevertheless, you can do a more quantitative analysis of these two simulations, and they agree fairly well. In particular, if you compare them at times where they have equally where the amount of gas in zinc particles is more or less the same here. So there's also something which is quite confident that at least two really different approaches converge to a certain level. As I said, there are differences which we link actually to the hydrodynamics and not so much to the implementation of the zinc particles. So what else can we do? Yeah, there's a nice simulation by Daniel Seyfried. So you can run the ideas, of course, if you implement zinc particles or use zinc particles, you can run your simulation for a long time and simulate, for instance, the disk evolution around a single star for quite a long time without going to higher and higher resolution, without essentially grinding your simulation to a halt. And this gives the possibility also to follow outflows, self-consistently launched outflows for quite a long time. And here's a simulation showing the velocity, the outflow velocity. Eventually it gets started, takes a while, and then you see how an outflow kind of evolves here and gets speed up and gets faster and faster over time. And eventually the gas is expelled from the surface of the disk. And this, as I said, this is not a subgrid model of the outflow. This is really a self-consistently driven outflow by the coupling of magnetic fields with the underlying disk which establish around the zinc particle. And you can do this, do an analysis actually of this simulation and ask yourself, because there's a classical theory of magnetocentrifugal launch. So essentially the gas is confined to, if you like, magnetic field lines, and you fling them around. The gas moves along the magnetic field line, eventually leaves the disk surface, which is called magnetocentrifugal launching. This was worked out by a seminal paper by Blanford and Payne in 82. And you can then patch the regions where your outflow is driven by this mechanism, or you can ask yourself, okay, I take essentially the entire Lorentz force. At the end of the day, the gas is of course accelerated by the Lorentz force, and ask yourself, this is the region where gas is accelerated, and this combines both the magnetocentrifugal launch and what is called the magnetic pressure launching, or magnetic tower launching. Yeah, and then of course I told you that you can use nicely the zinc particles, all the information. You have the accretion rate, you have the masses and so on, to use them as a subgrid model for feedback. And I will show you a couple of examples. Some of them are quite preliminary, but here we implemented this is not a self-consistent outflow, what we will see here in this collapse of a turbulent cloud core, but a feedback model, a subgrid model linked to the zinc particles. And you can kind of see how gas is accelerated essentially from the region where you form stars or protostars. And this is a fairly crude model, which I also recommend to you to use. There is a rough implementation of such a model in the Flash directory tree here. So this is a model which links essentially accretion rate. The momentum ejection is linked to the accretion rate, and at this time the opening angle was constant for all the particles, which you can also, as I said, can improve by linking it to the internal spin, for instance, of your zinc particle. Yeah, and there's something I will talk about tomorrow a little bit more in detail. You can use them, all the information of your zinc particles, to also do a feedback by radiation, ionizing radiation, because you know the mass, you can calculate the UV flux you expect from particular protostars here, and then feedback not momentum, but essentially pressure in this case, so you heat up the gas by ionizing radiation. And this is something we have seen earlier on, but here we explode these stars essentially, so they go off supernovae eventually, and this is also something you can fairly, if you like, easily implement, because all the information you need to more or less produce a roughly self-consistent model are stored in these zinc particles. There's another example, of course. Maybe on smaller scale, it might be interesting if you do, for instance, planet dynamics or so. You want to also see implement something like a drag force from the gas onto the zinc. So in this case, it's just a elastic scattering, and there's a couple of movies, so this is, the gas is moving, and eventually the zinc particle gets accelerated and gets to the same velocity than the gas. In a periodic box, it goes around, and here's the other way around, so that the zinc particle is moving, the box is still, and then of course the gas in the sphere of influence gets to the same velocity than the zinc particle. So these are just examples to motivate you that you can, if you have them once at hand, it's fairly easy to come up with your kind of own model of gas zinc particle interaction. Yeah, I mentioned this yesterday already. So there is an add-on to the manual in the directory doc zincs, and strangely enough, this manual has so this is something you find in your Flash tree, Flash hierarchy tree. Has the same name, that the add-on manual has the same name that the original manual, which is not distributed in the file I gave you, but it's in my home directory. So this is the 500-page Flash manual here. And if you want to do modification, this is essentially the main file in the zinc particle tree. It's called zinc create accrete, but it does, or at least from there, you can also spawn your favorite feedback or interaction model. So the modification should get into here. So here's a list again of the runtime parameters. I think most of them we already discussed. So you want to, of course, have to, most importantly, to essentially create things, you have to decide on the threshold density, which I told you depends on the resolution you want to use. And there's a couple of other quantities linked to the, for instance, to the advancing of the zinc particles and the gravitational interaction. So these are maybe the task or the setups you want to try out. This is the last slide here. So there are three stuff I can kind of recommend to you. So I told you that so in this rotating cloud core, the Bose-Bodenheimer test resides with the m=2 perturbation, where you form a couple of things. And you can also try this. I haven't tested this particular setup right now, but you're welcome to do so, and then we can figure out whether it works properly or not. Okay, that's about it for today. Thank you.